Can you guys hear me?
Yes, ma'am.
Yeah. Thank you. Let's just wait for like 5 minutes and see if everyone else can also join, and then we can get started.
Okay.
Okay, can you guys see my screen?
Yes, ma'am.
Okay. So feel free to interact with me because since it's going to be a project session, it's going to be very small number of people. I would like it if you guys can like speak up more and ask me doubts and pause me anytime, etc. So just seeing if we can wait for a couple more minutes so that a few more people can join before we begin. Okay, I think let's get started. So before we maybe move to the session, can you guys maybe like introduce yourself or at least let me know the type of background you guys are from so that I can see how to progress in the session? You can just unmute yourself and introduce yourself if that's okay. Okay, maybe I'll introduce myself first. My name is Sundari. I'm a PhD student at Srinivas Chakravarti Sir's lab. My thesis mainly dealt with um, designing computational networks specifically for understanding movement. And the aim there was if we could understand how normal movement is performed, if we damage the network, can we now see the network showing problems similar to what is experienced in stroke by people. So once we do that, can we then use or leverage that network to design and also decide better or more optimal rehabilitation therapies for patients? And yeah, I'm in my final year of PhD. I've just submitted my thesis. So yeah, that's about me. Maybe you guys can tell me a little bit about yourself. Okay, thank you, Dr. Akshita, for joining the session and for introducing yourself. Um, so, any of you here who have experience with neural networks, like you guys have built stuff from scratch, or you know how to build them, you know how to train them, etc.?
I may have done one. And I'm not from. Hi. I'm Tangaraj.
Hi, yeah,
So
hi.
my background is not from competition or anything. I have masters in neuroscience. I'm actually working in implants and in neuropathology. So as a hobby, I started coding, and then the beginning of this year, I did a small project creating a CNN network to um, basically to read the images, JPEG image of tumor files, and then diagnose the tumor. That was like a basic project using VGG network. Sorry, not VGG
Okay,
network, VGG model. Yeah, velocity
yeah,
geometry group.
okay, okay. Okay, so you have a little bit of experience with Python
Yes.
and coding and stuff.
Yeah.
Okay,
Yeah.
cool. Yeah, thank you. Thank you for joining the session. Anybody else? Abin, Krishna, or Anshul? Do you guys have any experience with coding or training a network?
Hello.
Yeah, yeah.
Yeah, hey, this is Krishna. I'm MTech PhD research scholar at IT Madras Department of Mathematics, and I have actually solving PD with deep learning. I have a little bit idea that is your work is slightly different from my work. Actually, my main work is the focus on PD, solving PD, higher dimension PD. But I have a little bit idea about these types of work. Main work is with neural network with physics. The, that is
When you say PD, you mean partial derivatives.
no, partial differential. PD means
Ah,
partial differential equation. Okay.
okay, okay.
OD
So I
means
thought,
ordinary differential equation.
right, I thought PD you meant Parkinson's disease for some reason.
Okay,
Sorry.
okay, great. Yeah.
Yeah, okay. Dr. Shubham. Ah, okay. Yes. Thank you. Okay. Since you guys feel a little shy, I guess, to introduce yourself, I'll just get started with the session. Okay. So today we're gonna see how to build a bilateral motor network for normal and stroke condition. It's going to be a very simple network. This is going to be very similar to what I covered in the forenoon session of day two. But there I discussed how to use CNNs, but today we're just going to stick with normal MLPs and see what happens or how you can use that in the motor domain and how you can introduce stroke and how you can rehabilitate it and all that. So I wanted the session to be broken down into like three major phases. The first phase will consist of three subphases, which will contain how are you going to set up an arm using equations and inverse kinematics, etc., to generate the data set that is necessary and use that data set to then code for and train an MLP model. This will be phase one. And then after that, we'll go for a short little break. And then after that, we'll introduce lesion in the network and see what happens when we lesion different parts of the network and also see how different sizes in different layers, how do they impact the network performance, etc. And the third part of the session will be how we can rehabilitate or get back the recovery of the network. There's no real problem statement or major problem statement that we will be dealing with, but this is kind of like the overview of what we're going to cover. And mostly everything that I'm covering here will be loosely based on this paper. I have also emailed you guys both the PDF of the paper and the link also. But I don't really have any slides prepared for today. I'm just going to use the paper to present it. I hope that should be okay. And you guys can interrupt me at any time to ask me questions of any kinds, both in the biology aspect or in the mathematical aspect or in the coding aspect. And yeah, so and also for most of the session, I will be putting you guys in breakout rooms and allowing you guys about like 2 to 5 minutes to figure like a very short problem by yourself using coding. You can definitely use AI or GPT to like help you guys code or create code chunks and then you can integrate that in the notebook. But after that, I will join you guys in the breakout rooms, and then we can like try to see things together. So the first thing that we're going to do is, okay, so I'll just make sure that you guys understand the problem statement better. So what we're trying to do is we're trying to see if we can create a network model that will accept a target or a goal location as input and generate the output from the network will basically be the joint angles that are going to be necessary to put the arm in a configuration such that it can reach to that target. If this makes sense. I'm going to assume that it made sense because you guys haven't said anything. I'm not really looking at chat. So if you want to interrupt me, just like go ahead and unmute yourself and talk. Okay. Movements are things that we all do on a day-to-day basis, right? All of us use our hands in multiple different ways in everyday life. But most often than not, most of these movements are goal-oriented or target-oriented. That is, what I mean is there is a particular goal and you're trying to reach to that goal or target. Now, let's say, just imagine that this is your arm and it's placed on a table somewhere, and you're trying to reach to a point from here to here. So, if we consider this as the arm, this will be your shoulder, this will be your elbow, and this will be your wrist. Now, this basically has certain angles that are going to define this configuration of the arm. One will be the elbow angle, and then two angles, one at the shoulder. So now, your brain does not really think in terms of coordinates. That is, okay, currently I'm at, say, my home position or rest position of XH, YH, ZH, and I have to go to a position of XB, YB, ZB. It does not plot it as, okay, let me move 2 units in X direction and 3 units in Y direction and no units in Z direction. Instead, you can think of it as the brain thinking in terms of joint angles. That is, it thinks about how much do I need to rotate my elbow or my shoulder and then which axis. It's based on this that it will give out excitations or signals to the muscle such that this angle configuration can be placed in the right way. Now, for this angle configuration, for each of these angles, you have um, two muscles that are governing each of these angles. Now, muscles can only perform one thing. That is, they can only contract. So, but if I have my arm outstretched in front of me and I slowly bend the elbow so that the wrist comes closer to my shoulder, that is called as a flexion movement at the elbow. And there is a muscle that is going to contract in order to create this movement, and another muscle that is just opposite to it that's going to relax in order to perform this movement. So, whatever activity that your movement that's going to, or your muscle that's going to flex is going to do, or contract is going to do, the opposite muscle or the complementary muscle is going to relax by the same amount in order to produce that movement. Does this make sense to everyone?
Yes.
Okay. Okay. So, like that, we have one pair of muscles for each of the angles. Therefore, we have three sets or three pairs of muscles for each of these three angles, one pair for the elbow and two pairs for the shoulder. So now we have this as the arm setup. Now we need to determine our workspace. That is, where is our arm in 3D space? Where is our target going to be? How do I generate the input? Now, in order to do that, you have to first fix the arm at a particular location in the XYZ coordinate. Now, I want you guys to concentrate on this picture here. So you can and visualize XYZ coordinate centered on your shoulder. For now, just focus on your right arm. So the x-axis will now denote the left or right direction, while the y-axis will denote the front or back direction, and the z-axis will denote the top or bottom directions. Now, this is how I'm going to define the x, y, and z coordinate spaces. And then once I've defined this, I'm going to see where I can place my human being itself. So now here, my person is going to be somewhere centered here with their head over here, and then the shoulder like this, and then the rest of the body. And this is going to be my rest position, where it's going to have some sort of value at the x-axis and the z-axis, but nothing in the y-axis. That's how it's going to be set up. Now, once I do this, I'm going to see how I'm going to find the trajectory for this. Does this make sense to everyone? Okay, I'm going to assume that it does. Okay, so in order to now calculate from or for a given set of muscle activations, what is my corresponding angle going to be? We're using these formulas. These are very well established formulas that are used in the field of robotics and in the field in other motor network research papers and experiments. So we're just going to adapt this thing. And then with these theta angles, we're going to see where our hand position and hand position is going to end up in. So it's with these two equations that we're going to get the actual position of the arm. So whatever activity the brain is going to send to the muscle will get plugged into these equations, which will give you the theta values. And then those values will then be used along with the rotation matrices in order to put into this equation here. Here, along with the rotation matrices that you get from the angles, we also have something called as H naught, E naught, S naught, etc. These are nothing but the starting position of the hand, the elbow, and the shoulder. So, with all of this in mind, this entire thing is called as the forward kinematics problem. That is, I have my muscle activations. Now, from my muscle activation, how do I get the end effector position? That is called as the forward kinematics problem. Now, this is what I want the network to do. I want my network to look at a target and tell me exactly the muscle activations that are going to be necessary in order to reach to that target. But now, in order to do this, I need to tackle the inverse problem to generate that data. Because when I'm generating the data, I'll have the position that I want my end effector to be in, but I don't know the muscle activations themselves, which is what I'm going to design my network to produce at the output layer. So to do that, I have to do inverse kinematics. So I'm not going to go too much into the mathematic details of how I'm going to set it up, but that's all there in the code itself. So we can just directly go to the code. Does anybody have any questions so far?
Yeah, why did you do the inverse thing?
Okay, so the forward thing is going to tell me for a specific set of muscle activations, what is my hand position going to be, right? So how I'm going to set up the network is the network will get a target position from the outside, and for that target position, it will give me muscle activations, correct?
Mhm.
But in order to train the network, which I'm going to train using supervised learning, I need to know this mapping. That is, for a given location, I need to know what the muscle activations required will be. Which is why I need to know the as a programmer, I need to know the inverse kinematic equations in order to generate that data set.
Okay.
So is it true that instead of saying muscle activation, we can say joint angles?
Yes, you can say that, but the network, at least the one that we're going to be training now, is going to be with muscle activations and not directly with joint angles. It's just to make it a little bit more realistic because from the brain, what you will get is the muscle activations and not the direct joint angles itself. But you can also do it directly from that, from the joint angle.
Joint angle is something we can define. I don't know how to intuitively understand muscle activation, even mathematically.
Ah, I understand. Okay. Okay. So I don't know how to explain it either. But yeah, you can consider it as output being the joint angles themselves. Okay. Okay, so then I think I'll go to the code. Okay, so first of all, we're just setting up the required libraries and the dependencies that are going to be necessary for this code. Some of them are just general purpose stuff. This is just for people who maybe are not super aware of like Python and Python programming, etc. But I mean, do stop me if you guys think this is unnecessary. But NumPy and math are just going to be your general purpose. Um,
Hello.
yeah, hi.
Yeah, you have not explored bilateral neural networks. What is difference between traditional neural networks and the proposed neural network? Have the proposed neural networks, and this is the existing?
No, the bilateral neural network I don't think exists anywhere else, but it's not a very fancy thing. It's just the way we are defining the architecture.
Yeah, yeah.
So
We go through that paper again and explore the networks. Is it possible?
yeah, sure. So bilateral, when I say bilateral, what I mean is usually in a neural network, if this is the input, the entire network gets both the inputs at the same time. But here, that's not what we're doing. We're basically dividing the network into two halves, and we're giving one set of inputs to one half and the other set of inputs to the other half. This is the reason we're calling it a bilateral network.
Have you used any activation function?
Yeah, we use sigmoid activation.
Okay, great. And what is the any optimizer you have used?
Atom optimizer.
Yeah, yeah. Adam, great, great.
Atom, yes,
And
yeah.
learning rate of this simulation?
Uh, I think I kept it at point 0.001. I'm not sure, but
Great.
the details should be present in the
I
GitHub
think
code that I shared with you.
this is the neural network, which is the I think first part you have what you have done. This is the different types neural networks, and another yellow color. What is the difference between these two colors?
So the blue color layers, this is actually a convolutional neural network. We're
Yeah.
not going to be seeing the convolutional neural network during today's session. We'll be seeing an MLP, but here the picture represents a convolutional neural network. So here the blue colors represent the convolutional layers and the yellow color represents the fully connected layers.
Okay. And what is the yeah? That is the green color something. What 2-bit HS input? What is this?
Yeah, so that is the hand selection input. So, for example, you know that there is a target in the workspace, but the network doesn't know which of the two arms to use to reach to that target. So, to specify that, we have something called as a HS input, which is just binary input. It'll either be 00, 01, 10, or 11. 0 meaning both the arms are at rest. 0 1 meaning the right arm is to perform the movement, 1 0 meaning left arm is to perform the movement, and 1 1 meaning both the arms need to perform the movement.
Okay. And 4 8 something that we have written, that is the number of neuron per layer.
That is number of the feature maps in each layer for the convolutional layers, and 50 30 are the number of neurons in each layer
Oh, okay,
in
okay,
the
okay.
fully connected layer.
Okay, 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 great. You can go through your next presentation.
Yeah, the code for this specific model was shared in the is present in the GitHub repo link that I shared via email just a while ago. So you guys can also look into that. However, the GitHub doesn't contain the input data set yet, but you can definitely go through the model itself, how I'm setting it up, how I'm training it, all that in that. Um, Yeah, anybody else? Any other questions? Okay. Okay. So here in this code block, I'm just importing all the required libraries that are going to be used in the rest of the network. We're going to be using Torch to uh, both create and train the network. And at a later part of the session, we're also going to introduce like a slider type UI element, which is going to be used to set the node that is going to set the layer that is going to be lesioned and the number of nodes that are going to be lesioned. That is why I have these two elements. Yeah. So, okay. Okay, so in this code block here, all I'm doing is I'm just setting up the inverse kinematic equations that I was talking about before in order to generate the data set. Almost until the end of this block is just setting that up. If you guys have time to go through it and you have any specific questions about this, you can let me know. But this is just direct mathematics, and I don't want to spend too much time on this because um, we also have a lot more things to cover, and this is just going to be the data set generation itself. So once we get this code done, uh, sorry, one second. Yeah, so once we get this code done, we have two other functions that are pretty important in this part of the code. The first is this function called as feasible points. So now the things that we have set up so far is we know what the network is going to be like. Like we know what input it's going to get, what output it's going to get. We know we know the specifics of our coordinate system. That is, what does X direction represent? What does Y direction represent? What does Z direction represent? Now, on top of this, we also know where is our eye going to be, where is our shoulder going to be, where is our elbow going to be, and where is our hand, the wrist joint going to be. Now, once we've defined this space, we need to now start looking into targets. Now, since here I'm only considering movement of the shoulder and the elbow, I can only consider targets within the reach of the arm. That is, if suppose you stretch your arm out, you can only reach to targets that are going to be uh, pretty close to your body. If you want to reach to targets that are going to be beyond your arm length, then you have to move your torso, that is bent forward in order to reach to that target. We are not considering these kinds of targets because we do not have a torso considered in the network. So, because of that, we need to filter and restrict our workspace from the entire 3D space to only include those points that are going to be less than whose distance is going to be less than the limb length. And we're also only considering the points that are in front of the subject and ignoring all the points that are behind the subject. And we're also going to make sure that these are all visible to both the eyes. Now, this is more of a relic from the CNN time. Like we don't need to perform this filtration anymore because we're going to use an MLP, which is directly gets the target. However, if we had a CNN, then it becomes necessary that the targets fall within the space of the eyes. That is the visibility area of the eye, and then only get the points. So that's what this function is going to do. Now, once that is done, it's going to send it to this function called as generate bilateral stereo data set with conditions. Now, this function is going to generate the workspace or the um, data set for all four of these conditions that I've considered here. 1, 1, 0, 1, 1, 0, and 0, 0. Does this make sense? Any questions here?
Are these the 2 bit hand
Yes,
signal input?
yes, yes. That's what these two are.
Okay.
So based on that, my data will also vary. So for 1-1, both the arms are going to be active, right, to that target. So both the arms will give out some sort of activity. Whereas in 0-0, both the arms are inactive. So they're not going to make a movement. So that's what this function is going to do. Yeah. And the next functions are just plotting functions to see how the workspace is defined, etc. Yeah. Did anyone have any doubts? Okay. Okay. So in the next part of the code, I'm going to use all the functions that I've defined previously. That is my inverse kinematics, my plotting function, my filtration function, all of that to create my workspace. So to do that, I'm going to bound my workspace first. That is, it's going to range from these values on the X direction, Y direction, and Z direction. Once I do that, then I'm going to filter it based on whether it's reachable, whether it's visible to both the eyes, etc., and then send it to my bilateral stereo data set with conditions and generate the workspace or muzzle activations necessary to reach those filtered points with the different arm conditions that I was talking about. So if we run this is basically telling you the some of the logistics or some of the particulars of this thing. I initially sampled about 20,000 points from the data set. However, out of this, only some 4,000 points were reachable, out of which only 3,000 were visible. And then after inverse kinematics was performed, this scaled down to 1,987 points. Now, the reason why this is 6 is because it's just XYZ coordinates, one copy for the left arm and another copy for the right arm. That's why it's comma 6. And the Y base shape is 12 because they contain the 6 muzzle activations that are required by the left arm and 6 muzzle activations required by the right arm to reach to those targets. And this 1987 will now need to be repeated 4 times in order to get our the 4 conditions set. And with that in place, the final data set is going to be 7,948. So this is the visualization of the workspace. And yeah, just this is just a sample for what it looks like when the arm reaches to the network. So here you can see that this is the shoulder point, this is the elbow point, and this is the wrist point, and this is where the target is present, and this is for the right arm, whereas this is for the left arm. So any questions so far? I'm asking because I'm going to like sort you guys out into breakout rooms in a little bit. So if you guys have any doubts, ask me now. Otherwise, we can proceed. Okay. So I think you guys are okay. So yeah, okay. So next we're going to go to the MLP training part. Okay, here what I want you guys to do is you don't have to worry about this biorobotics data set thing. I'll put you guys into breakout rooms of let's say there's 14 of you, so 3 to 4 people in a room. And I want you guys to look into both these neural networks, simple integrated brain and bilateral split brain. So now, just 1 second. So now you guys just go through this code, see what you understand about the architecture, and see if you guys can maybe come up with a different architecture that you guys would like to try out for this problem. So you already know the problem statement. You know that the network will receive input as the target, and it has to give the output as the muzzle activation. So now I'm giving you guys freedom. You put the architecture of the MLP in any way that you want to. Maybe don't mess with this block here. Get a new block here, and then you can start coding here. You don't worry too much about the syntax and stuff. You can just copy the same function and just change these layers. Like you can play around with the dimension or with how the layers connect to each other, etc., and then see how it goes. Okay, so I'm gonna stop sharing now. Uh, is that okay? Like, can I go ahead and put you guys in breakout rooms? Okay, so yeah, any problems? Okay, I'll put you guys in four different breakout rooms. Just try for like maybe 5 minutes or so and discuss among yourself. After that, I'll come through to each breakout room and discuss with you guys. Then after that, all of us can come back together to this. Okay, see you in a bit.
in between.
Hello? Hello? Can you guys hear me?
Hello, ma'am.
Yeah, hi. Can you guys just tell me what you guys understood or what you guys are trying to do, etc.?
So we are trying to understand the data. It looks like a synthetic data,
Yeah, it is. Yes.
and there is two checkpoints: reachability, visibility.
Mm.
Okay, and can you tell me how the input data works here?
Can you like maybe share your screen so that you can like point to something and ask me what it is that you would like
Okay,
to know?
sorry, ma'am. I'm using PC for
Uh,
running call
okay,
and
okay.
mobile
I'm
phone
using
for.
mobile data, ma'am, actually.
Okay, then I'll share the screen. You guys can tell me what it is that you specifically want to know. Is that okay?
Okay.
Yeah. Okay. Yeah. Tell me. What would you
Yes.
guys like to understand in this specifically?
So how the input data works here?
Okay. Okay. So before we go into the code, I'm going to tell you how the system is going to work in the brain. Okay.
Okay.
So there's two main players here in the brain. One is the prefrontal cortex, and the other is the motor cortex. Now, the prefrontal cortex will tell you, hey, you're thirsty, reach to the bottle. Okay. So you can see that the bottle is right in front of you. Now, the motor cortex has to decide how to make the arm reach to the target, right?
Okay.
Yeah. So the motor cortex will send out activations through neurons through the spinal cord. Okay. Now, from that spinal cord, the motor neurons will again go out and connect to the muscle. So think about it as the muscles like being like a spring and the motor neurons themselves being like some sort of a wire. Okay. And the wire is basically telling the spring how much it needs to contract or expand. Okay. Now, this level of contraction or expansion that the spring needs to do, that is what your muscle activations are.
Okay.
Does this make sense?
Okay, it's clear.
Yeah.
Yeah, so this is what your network is basically doing. The network is trying to see for this particular target, how much should I tell each of the springs to expand or contract. So in that sense, it is a very synthetic data, but this kind of system is what is used by robotics and in a very crude manner also by the human body itself. Okay.
Okay.
So, okay.
Ma'am, can you
Any,
tell me about the training loop used here?
yeah, okay. Yeah, this train brain, this one, right? Training phase, this one.
Yeah. Yes, yes.
Okay, so basically what it will do is for epoch in range of, so this loop, whatever is coming below is going to run for the number of epochs that you have defined. Okay, so at first it's going to start the training and it's just setting the training loss to be 0 at one point. Okay, at the initial thing. Then it's going to start taking the inputs and the targets. The targets here do not mean the target positions or the goal position. The targets here are the output targets.
Okay.
Uh, Desired output or desired muscle activations. Okay, that the network has to give as output. Okay, then after that, you basically set the gradient of the optimizer to 0 because this is how you're initializing it from the previous one. And then after that, you send the input into the model. Once you send the input to the model, the input will give you something as the output. Now that output is compared with the desired output to get the loss. Then this loss is back propagated and the optimizer, based on the loss obtained, will adjust the weights. Okay. Now, in order for you to understand how is the loss progressing, you are just adding this loss to this total train loss and you're appending it to this history. So this will calculate it for each of the inputs, and the total train loss will give you the loss that was experienced. That is the how badly did the network perform at each target for the first epoch, and then again for each target for the second epoch. And if your training is set up well, and if it is performing well, then with each epoch, this loss is going to keep decreasing. And that is what you will hope for. Does
Okay.
this make sense so far?
Yeah, ma'am.
Okay. Now the same thing, along with this training phase, I also have something called as a validation phase. This is basically where so you have the data now, but you don't want the network to just mug up the data that you give it. So in order to prevent this, you will split the data into two proportions. Usually the split is 80-20, 80% for training and 20% for performing a function called validation, where you don't train the network, you just give that validation input to the model, look at what the output is and compare it with the desired output. And then you'll see how that trained network is working on data that it has never seen before. This is just to ensure that the data does not, or the network does not mug up on the data that was given to it. Okay, and you're basically just calculating the error here, which is what is called as loss, and then you'll append it just so that you can look at the plot later. So that's how the training loop is set up so far. Does this make sense? So when you define a function like this, like you define it and then you have these variables here, those are going to be the inputs to the function. That is, when you're calling that function, you're also going to pass these as values that the function will use. Now, if I have these things set to a certain value, that basically means that those are default values. So unless I specify the epoch to be a certain specific number, it's going to assume a default value of 40. Same thing with learning rate and same thing with which device to use. Now, this argument becomes important when you have a very big network and you want to use a GPU to run or train the network. So, yeah. Any other questions?
Ma'am, do you stop here, ma'am, to prevent the model to
Overfit.
overfit the data?
Yeah. So that you can see. So, okay, if you look at my screen now, I have my train error and validation error, right? So this was just on the network that I already previously wrote for and I trained. And here, if you want, you can stop the training early so that it doesn't overfit. And you will see the overfitting when the training error is very small, but the validation error starts increasing. Here also you can see that it's slightly oscillating. So if you want, you can try and stop the training a little early. So instead of going to like epoch 20, you can try like stopping it at epoch 10 or epoch 15 itself.
Ma'am, but then you're forcing the model to stop, right, ma'am? Like, wouldn't it, how do I say, interfere with the result?
Yes, it definitely will. So that is a call that you have to make. So these are called hyperparameters. So the number of epochs that you choose, the learning rate, all that, you have to strike a balance with that. You make sure that the performance doesn't deteriorate, but at the same time, it doesn't mug up or overfit to this test data so much so that when it goes out and faces new data, it performs really badly, which is also bad. And in fact, if you think about stroke rehabilitation, this has very good analogy because in the last time I was talking about task-based rehabilitation versus exploratory rehabilitation. This is exactly what is seen in humans in that case, where they're given therapy under certain tasks and they get very good at performing those tasks, but they're not able to perform any everyday movements. Like, for example, if they're made to learn how to comb their hair or eat food or button up their shirt, these are very necessary movements and movements that they're going to use in daily life. But if they might get very good at it, but they might not be good at, let's say, writing or opening a door or anything like that. It doesn't translate, is what
So
I
the
mean. So
training
you
doesn't
need to
translate.
Yes, exactly. So you have to make a call of where to stop the training or how to include this sort of a diversity somehow in the training so that it doesn't um, become tuned to just one particular aspect of the data. Does that make sense?
So do you call this as partially trained one, or what is it called?
Uh,
Partial trained model, ma'am?
no, I wouldn't call this a partially trained model because since uh, the loss is coming down to 10 power minus 3, 10 power minus 4. So it's not a partially trained model. It is a fully trained model. So yeah, I don't think I would call this a partially trained.
Okay, ma'am. Okay, fine.
Okay, ma'am. Hello.
Yeah, tell me. Go on.
How can we change the neural dimensions here? Means
Yeah,
the brain
okay.
capacity
In the network or in daily life?
in the network, suppose.
Okay.
If I want
Uh,
to learn study a bigger brain,
okay.
recover from stroke like that.
Yeah. Okay. So what you can do is you can do it here. So here I've given 8, 64, 64, 64, all that, right? You can try increasing those values. So the syntax of this is FC1 is going to be the name of the layer and 8 is the input that is going to go into the layer, while 64 denotes the output that's size of the output that's going to come out of the layer. So 64 is my actual dimension of the layer itself. So instead of 64, you can try and give it 128. But the only thing is you need to maintain consistency of what you give here as the output from one layer and as input to the next succeeding layer. Because what you get as output here is what is going to go as input here. If you don't maintain that, then it's going to create dimensionality issues. Okay. So you
Okay,
can play
ma'am.
around with these numbers. Just don't change these two values, this 8 and 12. Okay. Because your 8 denotes in input size. Um, output size. Okay, of the network itself. Just don't play with these two, but you can play with these intermediate values and then see what happens to the training. Like you can see trends of like, is it training quicker? Is it training slower, faster? All that you can see. So I'll stop the conversation here. You guys can try doing this for now, like play around with these numbers, both in this integrated brain model and in this split brain model, and see what you can do. And I have shared the notebook here. So maybe you guys can, you will hopefully have a copy of the notebook in your local system wherever, and you can try and run it there and see. Does that make sense?
Yes, ma'am.
Okay. So I'll see you guys in a little bit. Okay.
Okay.
Hello? Hello? Can you guys hear me?
Hi.
Yeah. Hi.
Actually, yeah. So I was running those codes.
Okay.
So I couldn't figure, I mean, how it was running. And I
Okay.
would create some plots which y-axis was error.
Okay. That's all
So I
right.
can,
Maybe you can present your screen to me and I can help you out with what you're trying to do. Does that make sense?
so I ran the entire snippets of code. Can you see my screen?
Yes, I can see your screen.
So I ran the codes, all the codes from top to bottom.
Wow. Okay. Okay.
Initially, there was some training. I mean, I didn't understand what it was training.
That's all right. Okay. Huh.
So actual training. This is where I mean, this code shows us if there is any lesion in any particular region or layer,
Mm,
there will be errors in.
yes.
Can you just
Corresponding.
explain me in this graph? I didn't understand this graph.
Okay. Uh, okay. So here, what you're trying to do is, okay, so this is a 3D plot, and each point in that 3D plot represents a target in the workspace. Okay, that is a goal position that the network is trying to reach towards, and the color represents the error that is experienced while trying to make reaching movements to that. Now, you're introducing a lesion. Now, the title tells you what type of model you're using, which layer you're lesioning, how big a lesion you're creating, and the arm that is whose workspace you're plotting. So, split brain indicates the name of the model that you're creating the lesions in. ENCL is the layer name. If I'm not wrong, if you go a little bit above that, ENCL will be the input layer of the split brain model on the left side.
So this is
Okay.
the error. I mean, if it's coming towards yellow, that means it is creating larger error. And
Yes,
if it is
exactly.
towards the purple or blue, then it is less error.
Less error. Yes. So
So does
if you
that
just scroll, yeah. Sorry, go on.
so does this depends upon the magnitude of lesion?
Yes, exactly. So if you just scroll a little bit up, you can look at the slider that's attached. Yeah. So just come down a little bit. Yeah, you can see layer ENCL. You can see that, right? Yeah. So from there, you can slide the slider more towards the right. So that will keep lesioning the thing. And if you just pause it for a bit, see, it's changing now. So it will tell you how it's going to differentiate or how it's going to create an issue when there is a lesion of like very high value, all of that, and how that's going to affect the performance of the apps. So that's
But if
what
I
is.
increase the lesion fraction, so
Mm.
the error is going down, I guess. I mean, more of blue dots coming up.
So you're creating the lesion in the very first layer as soon as you get the input. So that will affect the entire layer. So this is probably why this is happening. You can try with a different layer. Just go to that layer drop down menu and maybe pick DCL.
DCL.
Yeah, that's the decoder layer. So now you can try
Okay. That's
increasing
the
the lesion size and see. Yeah, So now you can see that as the lesion size increases, the number of points that are experiencing the error increases. Right arm is going to remain the same because you're only creating the lesion in the layer that's connected specifically to just the left arm.
Okay. So as we increase, so we are expecting more of green and yellow points,
Yeah,
right?
yeah, exactly.
And this is going to be unaffected, remain unaffected, I guess. Yeah, it's great. So only the right side is changing. This one is right side, right?
This one is left side. Only the left arm is changing, while the right arm will remain the same because you're creating the lesion on the left side of the network, which is what
Okay,
is.
okay. It's not like human body where left and right crossover. It's like
We just thought that might complicate the architecture more, but you can try doing that. I mean, I've given the network there. You can try doing the contralateral thing. Just scroll a little bit up. I'll tell you where you can try and change the training. What about others? Any of you guys running the code? Anybody having any issues? Chetan, Sumit, Krishna.
I'm trying to change the electrics in the architecture, but I
It,
haven't tried for the laser.
no, that is all right. That you can come to later. Now, right now, you can just try changing the architecture and seeing the training and all that.
So I'm doing that.
Okay.
so. I didn't understand this rehab clinic. I think
That
it's
is all
showing some.
right. We'll come back to that a little later. Chetan, maybe you can work along with Dr. Shubham and see if you guys can do the architecture changing and the training thing together.
Can you let me know how to do that architecture changing? What is the code?
Yeah, just
It
go a
is
little bit
skills.
above. Yeah, it should be in phase uh, 2.
After changing the architecture, I can run
Yeah,
more code,
right
right?
there. Sorry, yeah, just 1 second, Chetan. Yeah, in phase 2, you can look at MLP training. That's where the network is. So you can just go through that a little bit and see what you understand. And then there you can change the architecture. Yeah, Chetan, what's up?
Like, after changing the architecture,
In
I can.
MLP training, in an MLP training, you have to change.
Yes, correct.
So how to change this architecture here?
Uh, I would really like it if you guys can work together. Chetan, if this is the same thing that you guys are working on, can you guys work together?
Okay, we'll discuss.
Yeah. Sumit, you too. I haven't heard anything from you. So you guys just go through that code block and I'll just see the other breakout rooms a little bit and then I'll come back here. Yeah?
Change what types of change? Like you should change activation function. We can change like optimizer. Which types change you want?
It's up to you. You can decide to do whatever you want to do. You can
And
change the architecture, you can change.
architecture means what? Like activation function, like optimizer, like another things. What types of architecture? Like hidden layers and
Yeah,
which
I'm leaving that up to you guys. You can decide what type of change you want to try it and see. Like, do you want to include more layers or more nodes in each layer? That kind of stuff you can try. Okay. This is just to see if you guys can like come up with a
no, like
MLP
we
code.
can change activation function. We can change also optimizer.
Yes, yes, yeah, up to you.
Okay.
Okay. Yeah, I'll just be back in a little bit. Okay. Thank you. Hello?
Yeah. Hi, Sundari.
Hello. Hi. You work on motor science, right? Raj Kumari.
Oh, yes, yes, yes. Yeah.
Yeah, I read your SOP, so I just got to know. Sorry, doing a little stalking.
Oh, yes, yeah, Sundari. I just didn't get a time to introduce myself at the beginning. I was just starting and just joined at that time. I'm working with Professor Meeta Kanikar at IIT Bombay, and my work is on understanding the role of cognition and motor control. So we do like experimental, we collect behavioral data and physiological data in form of EMG from participants. But yeah, and I use like a lot of MATLAB to do signal processing of the kind of data that we have got, but not like I've not touched this part of this side of neuroscience, creating MLPs or areas. So this is new and exciting. Really enjoyed. Yeah.
Okay, okay, I understand. So what about Riti? What about you?
Hi. So I am a PhD scholar in IIT Hyderabad and under Dr. Neeraj Kumar, and
Okay,
we are also working on how we learn motor movements and like in motor learning and motor memory. So I in particular deal with TMS. So I conduct
oh,
behavioral experiments while stimulating the TMS. So the like formulating models of neural networks is a bit new for me as well. So we both were
okay.
just trying to figure out the code first,
Can you
and
one
we
of you like share the screen maybe so that I can also see what you guys are working on, and if there's any help that I can provide, I can do that.
um,
Is that okay?
so yeah, we were not completely sure of what exactly we have to do.
That's all right. I can help you guys with that.
Okay, uh, Raj Kumari, can you just share the screen? Like,
Yeah,
so
I'll
we ran
share.
the code till the third till the phase, right?
Yes.
So we
Yeah,
can.
so Sundari, we have not done any changes or anything. Frankly speaking, we're just figuring out and we were understanding, what's happening and what was kind of expected from us. So I could see, I'll just tell my brief and then Riddhi can say what she has come up with. So I could see that you have used bilateral split brain and this is the architecture that you have formed. The first giving separate inputs to left and right and then merging them and then splitting them again for muscle control. So I was thinking that right now at this stage maybe something could be done. That the other architecture could be that at Motorhead right now we are giving different commands, right? It could be different and also shared. That is giving separate to left and right, and then there's a shared processing, and then the left has its own shared and the separate, and right also has the some sort of shared processing in the right. So what I want to say is right now this left and right feels like separate from each other, not they do not
Okay.
have any common thing. Like what
Hmm.
left is doing, right will not have information about it. But if we could encode this thing that the one arm knows about what other arm is doing, that kind of architecture could be built. I had a thinking on these lines that we can have here something like shared and separate for each arm.
Hey, that sounds like a good idea. Maybe you guys can try it out and see. Do you are you guys facing any specific difficulty with like coding it, or you guys are good to go?
We were just coming up with ideas. So the thing is,
Okay.
I think Raj
Yeah,
Kumari
so
also doesn't have uh, background in coding per se. So
Okay, I'll just give you like a quick thing of what you need to change, like what the syntax is like, so that you can play around with the code a little bit by yourself. You can stop sharing the screen. I'll share mine and I'll go over it with you guys. Yeah, just 1 second. Uh, Okay, so this is the network that you have here, right? So this basically is the name of your network. So when you're going to call your network, you're going to call it from this name here. Now, this def init function is going to be the function that initializes each of the layers that are going to be used in your network. Now, here, just like what you guys said, I'm just confirming what you guys said. You have two separate encoder layers, one for the left arm and one for the right arm. This will get the input or the target position that the left arm needs to go to, and this will get the target position that the right arm needs to go to. The reason why it's 4 is because it's X, Y, Z coordinate along with whether along with whether I should move the left arm or not. And same thing for the right one also. That's why it's full. Now, in the next thing, I'm putting shared layers. So, how this is going to be, this thing is self dot name of the layer is equal to nn dot the activation function that I'm going to use. This is just a linear layer, so linear, and then the input dimension, comma, output dimension. Okay, I'll just write this here. Layer name equal to nn dot linear input del, comma, output. Okay, so now if suppose you want to include one more shared or separate layer here, what you'll do is you'll do again, let's say self dot separate shared L equal to nn dot linear and uh, here you will do the input then comma output. Does this make sense? Now, one thing you have to make sure that you maintain here in order for consistency is the so this is the first layer, this is the second layer, right? This layer is going to be connected to this layer. So the dimension that I get here as the output should be the same as the dimension that I give here as the input. You have to maintain that in order to make sure that there is consistency in the matrix multiplications. You can think of this as how in matrix multiplication, you can only multiply two matrices when their sizes are matched with each other, right? Like m by m cross n can only be multiplied with any matrix that has n rows.
Correct,
So,
yes.
yeah. Okay, so you just have to make sure about that. And the rest of it is going to be the same in this function. Now, next in the forward function is how you're going to connect one layer to the other. Now, this HL is going to be the output that I get from the encoder layer. So here, what I'm doing is I take the input and I send it to the first layer here. And on top of that, I'm going to apply an activation function and I'm going to get the input. Now output. Now this output, I'm going to send to the next layer. So that is how I'm arranging or connecting one layer to the other layer. So if you now include another self-dot-separate shared L, then after this, whatever H shared I'm getting needs to go as input to that. One second, I'll just write it. Dot separate shared needs to get H shared as the input. Now, on top of this, I'm supposed to apply the activation function. Now, once I've applied the activation function, this is going to be the output from this thing. Now, this output needs to be connected to these motor heads instead of this head shared. Okay, so that's how I'll be writing the network. Does this make sense?
Yes.
If you have any doubts, you can ask me. It's not a problem. Okay, so maybe you guys can try out then with whatever.
I had another question.
Yeah, tell
Yeah.
me.
So in the same bilateral, one second. Yeah,
Sorry,
in the
in the
same
same what?
bilateral split brain, are we also include? Can I share my screen to ask?
Sure, please go ahead.
One second. Why is it only showing the entire screen? So here, what exactly is this doing? Like, is it encoding the feedback from the activation of muscle as well. Are we considering the feedback of the muscles?
Feedback from the muscles?
Yeah.
No. Okay. So the network is not a dynamic network. So I don't need to know feedback from what I did previously. So it's only
Okay.
going to give me so if I have my bottle, when I
Hmm.
reach my bottle, what is going to be the configuration of my arm? That is what it's going to give me. It's not going to give me the whole movement itself. So it's not currently using any feedback as
Oh,
such.
okay. Yeah, so my idea was revolving around that only, like if we can somehow
Oh,
introduce feedback, or
okay,
is it just the
okay.
feed forward mechanism or not? So
Yeah, currently it's just a feedback. Yeah, tell me.
yeah, that's about it. I mean, I could not speculate much
Okay.
about other things.
Okay, just try playing around with like the architecture itself and see how it trains and all of that. And once we come back from the breakout room, like maybe in like 8 minutes, I'll put you guys back in the main room and then we can see what happens. Yeah?
Okay, yeah, sure. Works, Sundari. Yes.
Sure.
Thank you. Okay. Uh, can you guys like tell me what all you guys did in the breakout rooms? And
Hello.
yeah, Krishna.
Yeah. Actually, I have done two changes.
Hmm,
First, I have changed activation function. Okay,
hmm.
like sigma
Okay.
8 to 10h, hyperbolic 10h, and I will also try to adaptive 10h. And second things I have changed Adam. You have used Adam optimizer. I have choose. I have changed Adam to. I have just change optimization. LBFGS optimizer and without learning rate. That is line search. Strong welfare I have changed. That three changes I have done, but I have no idea why your code is not working. Your code is I think someone has there is no any saving option. Due to this reason some
Yeah, you
error.
have to copy the notebook and make the changes in your version of it. That is why.
Oh, okay, no problem, but these two changes three changes I have done.
Okay.
And that is the yeah, in my case there is no learning rate, and strong welfare means that is learning rate is automatically one.
Okay. But any other like architecture changes, like in terms of the layer, like you
Yeah,
asked me the
I can.
question, right?
No, I have
Bilateral.
not tried, but I can change layer, number of layer and hidden layer. I can change and let this types of way I can do. Like you want to left, right, that another things I can hidden layer I can change. Any others like in like you have done in encoder, decode, encoder left some things. I can add some architecture like. Attraction we can add attraction site we can convert also in transformer, but it takes too much times like
Why do you
your
want to have a transformer?
yeah, transformer is the attention based networks.
I
uh,
know, but why do you need a transformer network here?
no, you want to tell me the change the networks like architecture. No, I think due to I have just this is not a possible, maybe wrong, maybe right. I'm just thinking about change architectures like modify networks. uh, that things no, so I'm telling about maybe
Okay.
it can be converted into novel platform, novel architecture. If just want to change like a hidden layer and that things is okay, that is no problem.
Okay. So the only aim that I wanted you guys to engage in this exercise is so that you can see, like, like if given a problem like this, and if you have the data set, like, will you be able to define a neural network and train it by yourself? That was the only thing. Everything else is up to you guys. Anyway, you guys are not going to get graded on this or anything. So, yeah, great that you tried so many different things, Krishna. Do try to see if you can make a copy of the notebook and try your changes in that. If in case even then it's not working, please let me know so I can see what the issue is.
No.
Okay.
Actually, just I have go through the link and I have changes, but actually your code was working. But I have no idea after you have just stopped presenting, and then automatically it is the I get some problems. I have no idea what happened to the code.
I understand. Just try to see if you can uh, download the code and then try to run it in your own collab, like open it in your collab or in like VS Code or some other systems if you have like that, then you can run
In
it.
GitHub, which folder your code is the in like a name of the uh,
No, not GitHub. I sent it on email. Just one second. I'll send the link here on the chat box.
okay.
Just give me a second. Yeah, I've sent the collab notebook link so you can
Okay,
try
okay.
it in. Yeah. Just download it and then try to make changes in that. Anybody else? I think when we spoke Um,
Oh,
Mr.
what? Hello,
Yeah,
am I audible?
yes.
Hey, what was your expectation? Like which types of changes I should do?
No, no, I don't have any expectation. I just meant if you, like, you asked me the question, right? Like, what is bilateral network? Like, why do you have something like that? So the network has that architecture. Now, if you want, you can play around with the numbers in that architecture and see how the training
Yeah,
progresses.
yeah. This is
That is all.
yeah. Okay, okay. This-
Yeah. Okay.
I was like,
Uh,
Ma'am, I've
uh,
tried with, sorry.
yes, you can.
Tangaraj, Mr. Tangaraj, I guess you
Ah,
can proceed. Yeah.
yes, ma'am.
Yeah.
I've tried increasing the epoch number, just like I've talked to you.
Okay. Okay.
So yeah, it went. The training data set, it was okay, ma'am. Uh, I increased to 50, not 50, 60.
Okay. Okay.
So, and then the training validation error was more, ma'am, actually.
Yeah. So it's probably starting to overfit.
Yes,
So
it
you
was one.
should. Oh, wow. Okay. Yeah. So you can try reducing that a little bit, or you can make learning rate very small so that even with a higher epoch, like the
Ah,
amount of learning it's going to do at each step could be reduced. You can try that. Or you can try with a more like smaller network and see. Instead of having hidden layer dimensions as 64, you can try with a more narrower network, like just 8
ma'am,
or
I have one question, ma'am. So, if you increase the hidden layers, what happens, ma'am? Like, if you increase the number of hidden layers, would it affect the training rate or better output or reduction in the error, or how does that affect?
so if you have more layers, the network should train a bit quicker. So with even just the smaller number of epochs, you should be able to see the network converging a little faster. Uh, and what was your other thing? Like if you made it smaller, on the other hand, it might take more epochs to learn.
Okay.
So, but you can try these things out. That was actually my expectation that maybe you guys will play around with these kinds of things and observe for yourself, like how is the changes and stuff. And
Ma'am,
in fact,
yeah,
yeah.
it takes time for me to code. So,
Okay,
uh,
okay, okay.
yeah.
I understand. Yeah. Well, you don't have to change much, though, I can tell you. But that's all right anyway. I mean, you can also try it out any other time when you guys have free time. So even after the workshop.
Okay.
So great. Yeah. Anything else you want to clarify, Mr. Thangara?
Ma'am, myself and Krishna, we were thinking if we
Yeah.
can increase the training in one hemisphere and reduce the training in other, would it be able? How? Where should you want to make changes if you want to uh, train one hemisphere more and one hemisphere less?
Okay, that is going to be a little bit tricky. In fact, I don't know how to do it in Torch, but usually there is a thing called trainable. There is a variable called trainable. And if you set trainable equal to true, then that means that layer will get trained. But if you set trainable equal to false, then that layer will not get trained. That is one way. But another way that we can do with our current network is by playing around with the conditions. Like, for example, when I put 0, 0, then I have the network just stay in that same position, right? It's not actually learning anything. Regardless of whatever target you get, it's not actually moving to it, it's just giving the same rest position over and over again. So here, you can modulate the conditions so that, let's say you want to train your left arm more than your right arm, then you can have the data set to have only conditions of 0, 0 and 1, 0. So the right arm is always under rest, while the left arm is either under rest or under movement. You can also include like 0, 0, 1, 0, and 1, 1, so that the network or the data set is skewed towards more training in the left side. You can try those kinds of techniques and see.
Just one clarification, ma'am. So if you want to make one layer not you switch off one layer, if you make it false one layer,
Mm,
so that
mm.
will affect both the hemispheres, isn't it, ma'am? Or is just
No, that will depend on the
in this code, I mean.
can just one second. Can you guys still hear me? Hello?
Yes, we can hear.
Yeah, just give me a second. Yeah. Hello. Hi. Sorry. Uh, in this code, how do we set only one layer to code or train? I'm sorry, I lost what you asked me.
No, ma'am.
Repeat it.
You
Yeah.
mentioned that if you make one layer false, I mean, like
Mm.
if you turn off
Trainable.
one layer while training,
Yeah. Mm.
yeah, trainable one. So wouldn't it affect both the hemispheres? Because I've seen like those layers were mentioned previously before you did the bilateral brain module, isn't it?
Yeah, so that will depend on which network you're going to use. Just one second, I'll present the screen.
Yes,
So
ma'am.
see, so there's actually two different types of networks here. One is the bilateral split brain, and the other is a simple integrated brain. Now, the simple integrated brain has no division. All of the layers will get all of the inputs and controls all of the outputs. Okay, so the input comes in, goes to the hidden layer and another hidden layer, and then gives the out. There is no segregation between one half versus the other half. Whereas in this bilateral split brain, you're having division in both the input and on the output side. So now let's suppose I'm setting the trainable equal to false in this shared layer here. Then, because the output from this shared layer is going to go to both the left and the right side, it's going to affect both my left and the right arm. Whereas if I just set the trainable equal to false as this layer, then it's only going to affect the left arm and it's not going to affect the right arm.
Okay, ma'am. Okay, ma'am. I understood. Thank you. Thank you.
Okay. Yeah. Any other questions? Chetan, I think you had unmuted previously.
I have just like a small idea, kind of like. Can I try that? Just let me know.
Yeah,
Uh,
sure.
so we are giving two separate inputs in our bilateral network, right? Like,
Mm.
so
Yes, one for the
can we
left and
have
one for the
some shared space, like some shared input? So how much I need to like change
shared.
for that?
Okay. If you're giving a shared input, then you'll have to use something like this model, simple integrated brain, where the input layers are shared between both arms. So you could have like a structure like, oh, sorry. Uh, yeah, you can have like a structure like this where you have the input, and this time you can just have four here. Four because x comma y comma z, or sorry, five, x comma y comma z plus whether it's 0 0 or 0 1 or 1 0 or 1 1. Okay, so it'll become let's call this left flag and right flag, whether I want to move my left arm or my right arm. Okay, now from here it will go to some hidden layer, and then it can go to uh, separate output layers where there is motor left and okay, I don't know how to play that, like a motor left and a motor right, or it can go to one single output like this. You could try something like that. Does that make sense?
Okay, okay, okay.
Sorry?
Okay, I will try that.
Yeah. Okay. 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 So I'll stop sharing again. And
No, no, no.
any
Actually,
particular.
yeah, actually, you're again a problem in code. I think you have you will we check once again. I think some error in code after.
what error exactly are you getting? And I want you to download the code and then
Yeah.
try it.
Yeah, I have tried, but something is missing. I think they are saying that.
At least like share your screen and do it. I don't understand the error you're facing.
Okay, just 1 minute.
In the meantime, like Chetan and Samraj, like you guys can try out the things that you discussed now. We'll get back to that in some time.
Hello, ma'am.
Yeah,
Hello.
yeah. Who's speaking?
It's Abin.
Yeah, tell me, Abhay, what's up?
Ma'am, I have a doubt.
Mm,
Current model is a static model, right?
yes. Yeah, it doesn't have any
And
dynamics yet. Yeah.
okay, it's using supervised learning also.
Yes.
Why don't we use RL for this? Because the real brain learn by trial and error, if I am correct.
Yeah, you can use RL, but we're not doing that because the main aim of the network is not to um, really understand by trial and error if it's going to reach to the target. But what I want to see is if I have a motor network, what happens if I damage the network and stuff. And if you think about it, most of the time, while we're performing reaching actions, specifically in a very familiar environment, we're not actually um, trying different types of movement before we decide, okay, this is the way I reach to the bottle. No, you look at the bottle and you make the movement to it, right? Which is less like RL and more like supervised learning, which is the reason why we went for this network
Okay,
instead
ma'am.
of RL.
I thought the relearning process in rehab where the patient does not know the correct muscle activation, but learns what the actually works to the practice, right?
Yeah, but there the problem is because there is damage to the motor network. It's not that they don't know how to, it's that they are unable to produce the necessary muscle activations to reach to that target because the number of neurons are going to get reduced or the number of active neurons are going to get reduced in the brain after a stroke.
Okay,
So
but we can implement a penalty for high energy use.
you could try, but all of that will increase the complexity of the network. In fact, the first network that we had with the sort of a stroke like thing did implement reinforcement learning, but the amount of time that it took to train the network was incredibly high because this is not
Okay,
going to be a discrete action space RL network. It's going to become a continuous action space RL network, which will increase the complexity of the code and also training won't be very straightforward. So
okay,
we
ma'am.
wanted to avoid all of that, and that's why we went for a very simplified network. But yes, reaching in some sense or the other, you can look at as a RL problem. And in fact, if any of you guys are attending the BG session tomorrow, she'll be talking a lot about RL based networks, and we used a very similar architecture only for reaching in our very first papers.
Okay, ma'am. Thank you.
Yeah, Krishna, what is the issue? Oh, okay. The rest of you, Krishna, can I get back to you in just a little bit? I'll just talk to the others and put them in breakout rooms, and then I'll come back to you. Okay? Krishna, you're on mute. I can't hear you. I'm hoping that you said okay. Anybody else have anything that they want to discuss? Raj Kumari and Riddhi, how was it, or how is it going for you guys?
We are still trying to make changes in the code, but we were not like able to implement it. So we'll just go. If probably you can just suggest the changes what you suggested to us in the breakout room, it will be easier for us to follow.
Then I'll put you guys again in breakout rooms. Like you guys can like try things back up again. And I'll just talk to Krishna and see what the issue is, and then I'll come back to you guys. Okay?
Okay, yes. Yeah.
Yeah, sure.
Okay. Yeah. Yeah, Krishna. Hi. Hello? You're on mute. Yes. Hi, Krishna. Yeah, tell
Hi.
me.
Is my skin is visible?
Yes, your screen is visible. Yeah.
What is the issue? I think something is missing in code, I think.
No, that's not possible. Just go up a little bit. In which cell are you having this problem?
I think
Okay,
this.
okay, 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 okay. I don't know why. 1 second.
No. Actually, I think after presentation, it was working, but I think someone has changed something. Then it will be not able to work.
Okay, just 1 second. I'll give you the function maybe, and you can try running it again.
Why?
I'm pasting the function that it's saying is missing in the chat box. I can't give it to you. Okay, in your code, can you check if it is available or not in the pre? Just go up a little bit. Yeah, in that feasible points. No, come down, come down. Okay, I'll send it to you on mail, okay? Because I'm not able to paste it in the chat here.
It possible to send a complete code. That is I will see what is going on.
Yeah, I'll download it and I'll send it to you. Can you just put your email ID here in the chat box?
I have sent. Now stop sharing here. Okay,
Um,
then you
yeah,
may send and I will check and I will let you know.
thank you.
Okay, thank you very much.
I've sent it to you.
Okay, great.
Hello? Rajkumari and Riti, can you guys hear me?
Yes. Sundari, yes.
Yes,
Yes.
okay. So tell me, what are you guys looking at or struggling with, etc.?
Yeah, so Sundari was just I was trying to implement the discussion that we had earlier, and I was just trying to figure out using some Google search what could be the code to implement this. So I was just showing quickly that
Okay.
that if I'm going on the right lines,
Yeah, yeah,
is my
sure.
screen visible to you?
Just starting up now. Yes. Okay.
Is it visible? Yes. So, something, yeah. So, right now, as I already told, right, that I want that the motor input should have two, that it's taking its own and also the input and the shared one. So, I've just, for example, I defined let the motor input be the hidden dimension and the half dimension from the above. And then I was trying to figure out, okay, this, the self motor lift that you have said. So, now having this that we can have both the inputs and having this ReLU, and now the dimension will become 6 because it's the 4 and also the 2 from the half dimension, and this is how self motor left and self motor right. Like, am I on the right track? Is this going okay?
Why are you defining it as a NN dot sequential thing?
A sequential, this is, I just Google searched about it and it showed me like this, because it has like many layers, that's why. Or shall I go just with n and linear? That's all right.
NN linear should be okay. That will make it a bit more straightforward for you also.
Okay.
So just do give
Yes,
one
so I
second.
just okay. I think
So
then we
just
require some
just
help.
just tell me what it is that you want it to do. So you want the input now, or tell me how you want the architecture to look like. Like you have the shared layer. Now from
Yes.
that, what kind of layer do you want?
Okay, so what I want is that at the motor head, I want the input from the shared layer and also the input from the. Okay, so I want the motor left to get input from the shared layer and also its own input. So that left has the information about its own position and also what right is where the right is. This is what I want.
Okay, then in that case, you don't actually have to change anything else. You can just expand the size of the input here. Okay, so instead of having hidden dim, you can have hidden dim plus half dim.
How?
Okay, yeah. Maybe you can have that as a separate variable, like
Okay, should I
maybe
say that?
motor in and then
Okay, as I said, like I guess.
motor dim. Yeah, okay, motor in anything equal to hidden dim plus half dim. The spelling error there in hidden. Yeah, yeah. And you can have nn dot linear motor dim. Same thing in the next one also. You can have it as motor dim. Now, what you have to do is in your forward function,
Right.
just come down a little bit. Yeah. So in this, when you're sending the input to self.motor.left, instead of just giving h shared, you can do torch.cat and you can put h shared, comma hl or hr. So like that, you'll have to have two variables, one for input to the out L and one for input to out R. And you can try.
Okay,
So
right.
you can just say inp L equal to
Okay, here, right? Or here at
right
the bottom.
before phi dot split outputs motor command.
I have it here, yes.
Yeah. In IMP underscore L.
Sundari, are
equal
you
to,
there? That's right.
yeah, it's correct only. Please go ahead.
Correct, no?
Actually, AI actually showed you the correct one. Anyway, equal to torch dot cat. Yeah, yeah. Torch dot cat. Just follow what it's telling you. Torch dot cat. Yeah. Head shed, comma head shed. Correct.
Can I just
Yeah.
it is showing me how to accept this. Are you aware? Like, it
Tab,
is
tab,
tab.
tab. Just press tab. Yeah.
Oh, perfect. Yes, I was just putting because in MATLAB
Yeah.
you have this right arrow, now the right arrow was not working.
Oh, yeah. I understand. So now you've defined the input, right? You have to now connect this input to the layer. So here you do, so you have out L equal to, right? So self dot motor left, in brackets, instead of doing H shed, you have to do inf L and inf R. That's all. Yeah. Okay. So I'm going to leave you guys here now. You can try training this and you let me know what the performance looks like.
Sure,
Okay?
Sundari. Yeah, that was
Yeah.
of great help. Thank you so much.
Sure. Okay. See you guys in a bit.
Yes.
Hello? Chetan? I don't remember what question you asked me in the previous thing. Yeah, hello? Can you hear me?
I asked about that React bridge. I'm working.
Okay. Okay, you can mute yourself. Let me talk to the other people here. Sumit and Dr. Akshita, what are you guys working on? Do you guys have any ideas that you need implementing or need help implementing, or are you guys feeling a little lost? Or hello? Yeah,
Hi. Yeah,
Doctor.
actually, I'm just trying to understand because I'm entirely from a different field. So I'm just
Okay.
observing what is happening. So I'm a little lost. So, but
Okay.
yeah,
So any
that's.
question or any doubts that you have for me, or
Actually, regarding the coding and the mathematical part, it's completely new for me. But still, I would like to ask about the, conceptual part. So, as far as I understand, we're trying to understand this in a, normal healthy brain. So, how it works on the, motor part. But since the topic also includes the stroke part, so can you give me an idea how what happens, what exactly happens?
you mean in the code or in the normal like brain?
Normal thing, yeah. And how do we understand through coding what happens?
Okay, so in the normal brain, basically, stroke is going to happen because of
Mm-hmm.
a vascular accident.
Yeah.
So either there's going to be a rupture in the blood vessel or there's going to be a blockage. So because of that, the blood flow to that particular or blood flow supplied by that vessel is going to stop. So the neurons that were previously getting blood supply from that vessel are now going to starve. And because they don't have any energy reserves, etc., they're going to die. And unlike other cells in the body, the neurons are not that quick to regenerate. So now you have a
Mm-hmm.
vacuum. So
Yeah.
the functionality that was being served by the neurons that have now
Correct.
died, that's going to be lost. And because of the way the brain is set up and because of the characteristics of the different blood vessels itself, the most commonly observed problem after a stroke is something called as hemiparesis, where
Yeah.
paresis means a weakness in making movements, and hemi is in one half of the body. So
Mm-hmm.
this is the broad picture of what we're trying to do with the network, or what we're trying to simulate with the network. Now, in the brain, what happens is as soon as there is a rupture or a neuronal death, um, there is a short period of time right after that, which lasts for about a few weeks to about 3 months. Is there is this window called window of plasticity, where the neurons are very active and they want to compensate for the death of certain neurons. So they do this by taking up the functionality of the neurons that were lost. But after this window of plasticity is lost, they become a little bit slower, or they become a little bit more passive in accepting this job. So we try to, as soon as the patient is stabilized, we try to introduce physiotherapy or treatment options to the patient as soon as possible, so that we can leverage this window of plasticity.
Okay.
So
So do we,
that's what happens.
okay.
Yeah.
Yeah.
Cool.
So we understand the normal neurons, like how we simulate them. That is what I understood. Are we trying to understand what happens in the stroke? So do the normal neurons take up the functionality of the damaged ones? So, or are we trying to understand the, simulation, what exactly happens, how um
Okay,
the
so
normal.
with our simulation, what we're trying to see is we are assuming that we can't do anything about the brain. The only thing that we can do is see how we can design the training regime so that we can get back the lost functionality. So with our network, we're trying to see how much of retraining or
Yeah.
what kind of retraining can I give so that the network can recover. That is
Okay.
what is the aim. Yeah.
All right. Okay. Okay.
Okay.
I think
Okay.
that's helpful. Thank you. Thank you so much.
Okay. No problem. And you can look at the code, and if you have any doubts even later on, you can still message me or
Yeah, yeah.
email me.
I will
Yeah.
take some time and yeah, maybe
Sure.
yeah.
Mm.
Thank you.
Okay. 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 Sumit, any problems, issues?
Uh, no, not as of now. So I added another layer, a
Okay.
bilateral brain, and trying to do that. Now, uh, okay, so it's just I wanted to, so I need to change the code mode. So now it's only doing the hidden layers, but I
Mm.
can't see, I can't visualize between the how it is changing between when it is only 2 layers or 3 layers. So now I need to add another
Okay.
separate that, yes. So that's what I'm
Okay.
trying to figure out. Yes.
Okay. 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 So you keep going ahead with that, and I'll check back in a little bit. Like I'll
Okay.
close the breakout rooms in some time, and then we can come back again. Okay.
Okay.
Just send me a message in case any of you are stuck and you need help with anything. Okay.
Okay. It's a, 1 second. Can you
Yes.
help me in one thing? So,
Yeah.
this might be a very silly question, but I'm trying
That's
to
all right.
understand this.
Mm.
So, the input is only 8 values. So, for the uh, bilateral brain, it's split into 4 and 4, but the output is 6 and 6. Now, what does this mean? Like, why is it more than the input value? Because nothing of
Okay.
that sort is going on with the simple integrated brain. So I was just a bit
No,
confused.
the simple integrated brain is going to accept an input size of 8 and give an output size of 12.
Okay, okay. So
So the
all of them are
number
getting,
6, yeah. So the number 6 is for the 6 muscles. I told you, right? We're trying to control 3 angles, one elbow angle and two shoulder angles. And each of these angles will be controlled by 2 muscles each. That's why it's six
okay,
muscles for
okay.
each arm. Yeah.
Each, okay, okay.
Okay.
And the, okay,
Yeah.
let's see. Thank-
Yeah. Okay. Okay. Hello? Tangaraj?
Ma'am, can you hear me?
Yes, I can hear you. So,
Ma'am,
did you try anything that we discussed? Yes.
yes, ma'am, I've tried, ma'am.
Okay.
So initially I stopped the shared layer.
Okay. How did you
So
stop it? By
uh,
trainable equal to false.
or I just put a hash before that.
Oh, no, no. That
That won't work, ma'am?
won't work. No.
No, ma'am.
That
What I
means,
did. Hmm.
can you show me what you did?
Yeah, 1 minute, ma'am. I'll show you.
Hmm.
Hmm. Wait, share screen. Ah, is it visible, ma'am?
Yeah. Yeah. It was visible now. Yeah.
Hmm.
Done.
So I
Okay.
I changed here, ma'am.
You've made self-taught motor, right? You've commented it, right?
Yes. So
Yeah, so that won't really affect the training. The
yeah, I
sense,
didn't change much.
yeah, so what you're doing here is you're changing the network itself so that it has only one shared layer instead of having two shared layers. So you're not really
So it
doing,
didn't change the training much.
yeah, I understand. So
So
this
if I were
won't
to put
help
it
you.
false, sorry, ma'am. If I were to put it false here,
Mm,
so let's say because I still want to have this copy of it. So I just thought like,
I understand.
so would this one work, ma'am?
One second. Will what work? What did you change? Sorry, I didn't.
So one minute.
Oh, no, even this will not really work. You can't really assign it like that. It will create problem when you're trying to back propagate because your false is like a
It's a Boolean
binary
value.
thing. Yeah,
Okay.
exactly. So this won't really work. So instead, you can try this. Um, you can try to see if you can put requires grad equal to false. So I'm just pasting something that Google is telling me. Just try to look at like Google for it or talk to GPT, Gemini, etc., and try to see if you can figure it out. Okay, you can try
Hmm.
and set requires grad equal to 0.
Request
Self-taught
grad.
linear dot weight requires grad equal to false. So just
Hmm.
Google it once, get the syntax, and try it and see.
Okay,
Okay,
ma'am. Okay. Hmm.
okay, okay. Cool. I'll see you guys in a bit. Okay.
Hmm.
Okay, so we're nearing the end of the session now. So I thought we can spend maybe 4 to 5 minutes just clarifying any doubts so far in either the code part or in the biology aspect of things, in both movement science to etc. Whatever I know or whatever I understand, I can clarify to you guys. And the rest of the time, I thought I'll quickly go through what the rest of the cells will do. So you guys can try it out in your own time and see, or if you want to, you can also reach out to me later offline to clarify more doubts or discuss any like new problem statements that you would like to pursue or look at, etc. Does this sound good? Okay, I'm gonna assume that it sounds good. So you guys can maybe tell me if there's any doubts that you guys have, like anything that you guys tried, it didn't work, or anything that you guys want to try and you're not sure about how to do it, anything like that. Even if it's a coding function, coding issue, you can still ask me. I don't mind.
Hi, Sundari.
Yeah, hi.
Yeah, Rajkumari here. So, Sundari, first of all, thank you. The session was very nice, and we implemented the changes you suggested, and the brain was trained. We were able to implement it correctly. I just wanted to know. Then I played with different epochs that we can have the different loops, and I was just looking at the training error and the validation error that was coming. So I just ran the architecture for like 100 epochs at the learning rate of 0.01 that was mentioned by default, and we were able to come to the error of something like 0.3 zeros and 1 6 etc. So my
Yeah.
question is, right now, this is the one architecture, and I just ran my model for it, and there was the original one that you had created. So like, what are the bases or parameters by which we can compare these two three architectures, or is it like, is this does this question make sense, whether this
Oh, it makes
architecture
total
is
sense.
better than other architecture?
Yeah, it makes total sense. So there's two types of ways in which you can compare whether one architecture is better than the other or not. The first thing is the training loss, validation loss, values that you're getting for each epoch. You can compare those. So you can plot the loss curve across epoch for different architectures and see how they are. The better thing to do would be to pick a model that is showing both smooth training and validation loss curves. That would be one way. The other way is by testing. So now you've trained the network. So next thing, what you will do is you will freeze the network and just give it inputs and see what the output is, and then compare that with the actual or desired output. Now, you should usually do this on data that the network has never seen before. So
Okay.
let's say you have the entire data set, right? You can divide it into three parts: one for training, one for validation, and one for testing. So during training, you will use the training and the validation data set. And then in the last part, you will use the test data set and see how the performance is. You can look at values like accuracy, etc., and usually select the one that has the highest accuracy. Does that make sense?
Yeah, this makes sense. Totally, this makes sense. Cool. Yeah, and just the follow-up question to this is, Sundari, that what about the learning rate? How to decide? Right now, you have given it as 0.01. Is this like norm in computational neuroscience, how the value is given, or there are some ranges that, depending upon the architecture or the kind of problem we are solving, the learning rate will differ?
The type of problem that you're using and the number of epochs that you have, all that will can play a role in learning rate. But most often, a value of about 0.001 should work. That's like what people usually use, and
Okay.
it seems to work for them. So yeah, you can try with that. If you feel like the network is taking too long to converge, or too long to get to a very small error value, then you can slightly increase the learning rate. But at the same time, if you make the learning rate too high, then the error value could start oscillating. That is, in one epoch, it can show reduced error, but in the next epoch, it can show high error, and it will keep doing that. So you can play around with these kinds of parameters. These are called hyperparameters. So you can play around with these hyperparameters to see which works best. There is no real one size fit all for these things.
Okay. Cool, cool. Yeah. Thank you.
Anybody else? Okay, if there's nobody else, then I'll just quickly present the rest of the code so that you guys can maybe at least try it out in your own time. So I think we stopped here where you had the network architecture, and then right after this code block, we had the training loop. And then after that, we had the phase three, where we load the data set and then put it into the type of format that your torch network is going to accept. And then we have the train brain function call, which is basically the training loop, where you give the model that you want to train and then the data set that it needs to train on, define the number of epochs, the learning rate, etc. So with all of this done, this is where you will play around with the epochs and the learning rate, etc. And then after that, once this is done, your brain is lesioned, or the brain is trained. Sorry. So once this is done, you currently have the healthy brain ready. Now you want to start looking at how you can introduce lesion. Now, in order to introduce lesion, you can't take the model definition as it was before, because you need to start including certain things which will decide which of the layers to you know Okay, so how we're going to introduce the lesion is by selecting a bunch of nodes in one or more layers of the network and setting the output of those nodes to zero. So to do that, I'm going to define something called masks. So those masks are like dictionaries where for each layer, I will decide which of those nodes to be set to zero. Now, let's say, for example, if I set the mask for the input layer to be, let's say 8. Okay. And the input layer is 8 size and I have 8 ones, then that means all of my 8 nodes in the input layer are active. Whereas if I set this to be 0, 0, and then say 0 here, then 3 out of the 8 nodes are set to be inactive or are lesioned. And it's going to be the second, third, and sixth neuron that I have killed. So by this, you will define the mask and you will decide which of those layers to be set to active. So currently, what I'm doing is I'm having like a interactive lesion thing, lesion slider thing, where if you do this, just one second, if you run this, Mhm. Sorry, I'm really sorry. So you, oh, it's not trained. So once you train this network, I'll just put it to 20 epochs now. And, oh, sorry. I'll just put it to 20 epochs now and I'll train it. So it once it starts training, so it will finish training. Yeah, okay. So that network is trained, right? Then you go and call the lesion slider thing on this network. It was the integrated brain thing that we trained. So, so you guys can still see my screen, I hope. So this drop-down menu basically helps you to decide whether you want to lesion layer 1 or layer 2. And let's say I'm trying to put the lesion on layer 1. And I'm trying to see, I'm trying to see how much fraction of lesion I can create. I'm going to create 80% lesion. So you can see that the graph now changes. Now, what is given in the graph is the title of the graph tells you the model that I am trying to create the lesion in. the layer that I'm going to create the lesion in, and how many nodes in that layer I've lesioned, and whether this particular plot is showing performance of the left arm or the right arm. Here, the plot itself is a 3D plot where each point represents a target in 3D space, and the color represents the error that is experienced when the left arm or the right arm reaches to that space. And as I keep increasing the lesion, the value of this error should keep going high. Now, because this is the integrated brain network, uh, regardless of which layer I create the lesion in, I'm going to see performance deteriorating in both the arms. Whereas in the split brain model, depending on which part of the brain, whether I'm creating a lesion in decoder left or decoder right, then the performance deterioration will happen in that corresponding arm. Now, Rajkumari and Riti actually tried one thing where even though the outputs themselves were connected to separate arms, both the output halves of the network still got input from both sides of the network. So now, if they created a lesion in that network, they should be able to see a problem in both the arms together. So that's what this lesion slider thing part of the code does. And the next part is the rehab clinic. So in this, I'm basically splitting the entire data sets into four different data sets with 1 1 condition, 0 1 condition, or 1 0 condition. And then, depending on which side of the lesion that I'm creating, I decide what type of retraining I want to do. So that you can, all of that you can define here, and you guys can basically see like which type of, which um, network I want to lesion, which layer I want to lesion, how much I want to lesion, and once I lesioned it, what kind of rehabilitation do I want to give? So I will change that here, whether I want to give like train 1 1 or train 1 0 or train 0 1, etc. Okay, so I'll stop sharing now because we're already beyond our timing. But this is basically the idea of the network. And I mean, I apologize that we couldn't really cover more than maybe like half the session for what I planned. But you guys can still feel free to go over the code. And if you guys have any doubts, you can still reach me offline, either through the WhatsApp number and there in the group, like my number should be there in the group, or through email using the email ID that I had mailed you guys today from. So if there's nothing, anything else you guys want to discuss, we can do so. If not, we can end the meeting.
Ma'am, thank you for the session, ma'am.
Yeah.
The same study, have they tried in Parkinson's disease, ma'am? Where depletion substantia nigra just affects the direct and indirect pathway. Do you know any sort of
No. Okay, so are you going to be attending the PG session tomorrow?
basal ganglia? Yes, ma'am.
Okay, so there she'll tell you how they're trying to look at what happens when there is, degeneration in the dopaminergic neurons. But we don't really look at physical therapy for PD. That is, we had some ideas of how we can do it, but we never really went forward with that model. But in our lab, we look at what happens during DBS or during what else? Medication like L-Dopa, if we produce to it, what kind of TPS and how much dosage of L-Dopa needs to be provided to get improvement. All that you guys will be seeing in, I mean, you at least specifically will be seeing in the BG session tomorrow. I can circulate some of the papers and the recording and the code books, everything will be available for all participants. So others also can take a look at it.
Ma'am, and another thing, ma'am, regarding the code, in the rehab clinic, there's some error, ma'am.
Oh, really?
Yes, ma'am, assertion error.
Okay, can you like copy paste the error that you're getting?
Yes, I mean, I got.
Okay, just copy paste the error that you're getting. Let
Ah,
me take a look at it and maybe I can circulate the corrected code book in a bit. Is that all right?
yes, ma'am.
Hello, ma'am.
Yeah. Hi.
Yeah, if we supposed
And
to
oh, just
want
one
to
second.
symbolize.
Just one
Yeah.
second. Others, if you guys are done and if you have nothing else to talk about, then you can exit the session. Yeah, sorry. Abin, you can tell me what's up.
Okay, ma'am. Suppose if I want to simulate a progressive disease like mm, ALS. Okay,
Progressive disease like?
ALS.
Okay.
So what changes I must have done in the code?
Oh, okay. So for that, progressively muscles start getting affected, right? So you will have to do it in stages. Like, for example, first create lesion in just the first layer and maybe like a 20% lesion, and then see how the model is, and then see how the retraining is and how the performance improves. And then after that, you can, like, progressively keep uh, increasing the size of your lesion and then keep simulating multiple rounds of retraining. But I'm not really sure what you would achieve with that. Since it's a progressive thing, therapy of this kind might not be very useful. But yeah,
Should I
this is a way you
increase?
could try.
Should,
Yeah,
should I increase the lesion fraction
yes, you should
progressively?
increase the lesion fraction. Yes, progressively. Yes.
Okay, thank you, ma'am.
Okay. Okay. Anybody else? Okay, if there's no other questions, then I'll end the session. I'll look into the assertion error that you guys had told me about, and I'll get the corrected notebook. And yeah, see you guys later. And if there's any other doubts, please feel free to reach out to me. Okay, thank you.